Now we have Laflamme.
Yeah, my name is Catherine Laflamme. I'm a research scientist at Fraunhofer. For those who don't know Fraunhofer, it's an applied research institution, I would say, and really focusing on using research that's developed at the university and bringing it to industry. So it's really at that transfer level. And that kind of brings me to the topic of my talk, which is explainability in reinforcement learning, which is a big topic when looking at industrial applications. And maybe in advance, it doesn't have anything to do with particle accelerators. My background is actually in physics, so my PhD is on quantum computers. And I was a summer student at CERN in 2009, I think. So it's kind of fun that I'm back at something to do with particle accelerators now, but my talk is on something a little bit different. But I hope that this topic of explainability is still something I think pretty interesting, so hopefully you can get something from this. I think in this audience, I don't even really need to go into this. Yeah, there's big success stories for reinforcement learning. That was kind of at the time when I was starting at Fraunhofer, and I was thinking like, okay, it's an interesting method, and where can we use this in industrial applications? And can it have that kind of success that it saw in those kind of computer game situations? Since then, we've worked on it in a couple different like use cases, job shop scheduling, matrix production planning, routing in a production environment, energy management systems are a couple of examples. I won't go into them in detail today, but you can ask questions if you're interested. But the point was that, like, through all these projects, I kind of started to see there's some open questions still for these practical implementations of reinforcement learning. And one is that, like, if you're working with a company, they'll come and be like, okay, yeah, but what will I get from it? You need to be able to say in advance, and it makes sense, where will this method be advantageous with respect to, for example, heuristics, which are used a lot in these kind of control optimization problems. A second kind of open problem is the simulation problem. First of all, a lot of companies are still struggling to have, their databases, so to collect enough data to develop simulations or digital twins. And even when you have that, you still have this big real world gap. And the third one is that companies are not, at least in Austria, so that's where I'm working, aren't necessarily ready to implement neural networks in their control software. There's a lack of transparency, there's a lack of explainability, there's this new AI Act coming into play now, there's no standard process on how to do that, and there's just not a lot of acceptance, experience working with neural networks, and so there's just a lot of it's pretty slow, I think, to get there. They're probably, we will get there at some point, but it's just not realistic at the moment. And in kind of the work I'm doing, I'm kind of trying to look at all of these kind of questions and try and find, explore solutions in all of them. Today, my talk is on the third one. So it's really looking at this lack of transparency and lack of explainability with reinforcement learning because of the neural network in the background. So that brings me to my research question. Can we still benefit from reinforcement learning if we're not going to implement a neural network in the end? And to what extent can we do that? The use case that I have, it's a pretty simple use case, but we heard in one of the talks at the beginning, one of the keynotes, boring problems aren't necessarily bad. The reason for this use case is that, I forgot to mention at the beginning, all the project partners in this project, one of them is Bosch, and this powertrain control use case is a problem that they're very well familiar with. They kind of know it inside out. They have a standard solution, and it makes it easy for us to just kind of demonstrate feasibility for this project. Our aim isn't to create like the best solution for this exact problem to implement it. We just want to understand in the end how to use, we're going to be training decision trees, how well that could work in the future. So what is this use case? In particular, it's going to be to find optimal gear shifting logic for an automatic drive vehicle. How does it look like? It's in this kind of diagram down below. You start with a driving cycle, and that's just some reference velocity your car wants to follow. You have a driver who sees that reference velocity and pushes the pedal or the brake to try and follow it. And that information goes to a control unit. And the way the control units are implemented now, it's usually a lookup table. And that lookup table is developed by application engineers. How they exactly develop this, I don't know all the details, but it's a lot of previous experience. They have their own ways of testing it. They have then hardware and loop testing. They come back, they try again, and they develop a lookup table, which is encoded in this control unit. That goes to the transmission, it changes the gear, and you start again. idea is to replace that control unit with a reinforcement learning agent, but with the caveat we can't implement a neural network policy in the end. All of this is built on, we are using a MATLAB simulation for this. Like I said, our project partners at Bosch, they have internally their own simulations, which they use for testing. But this is also a real world problem. We don't have access to their simulations. In order for me to get internal access, that would have been a really long road. And these Simulink simulations are close enough, and it replicates kind of the way they work. So it's not too important in the end. So that's why we chose this MATLAB simulation. It's basically a full vehicle model. It's got the engine, transmission, everything that you need. And this is how it, so for anyone who's used Simulink simulations, this is how it looks like. On the left-hand side, you have the driving cycle as one of the inputs, where you give that reference velocity. Then you have the driver, which generates the acceleration and braking commands. Then you have the control unit, which has the transmission control module in it. And down below into the simulation, you can kind of adapt it so that you can override that transmission control with your own input. And at that's where we want to kind of dock on with our reinforcement learning based policy. What do we use as a benchmark? In this case, we use the MATLAB, or what's implemented in MATLAB, their optimization. They take as inputs for their optimized controller vehicle speed, pedal position, and the current gear. It's not so important to read this table exactly, but this basically gives you, depending on what gear you're in now, if you're speeding up or slowing down, to what gear you should shift based on the pedal position. And so that's what we'll use to kind of rate our agent or our policy on how good we are. And we're going to be using then the exact same input variables as our state space. So we have a dimension 3, the vehicle speed, pedal position, and current gear. How are we going to evaluate how good our policy is? We have two criteria. The first one is fuel economy, which is for us the total distance divided by the total fuel accumulated across the complete driving cycle. So here you see it as a function of time, but we take the last value on this plot because that's accumulated and averaged over the entire driving cycle. Here's a warning because this is in miles per gallon, which you want it to be high. In Europe, you're often going for the liters per 100 kilometers, I think, which you want to be low, but we're trying to increase the fuel economy. And then we want to kind of trade that off with the velocity following, because obviously the best for the fuel economy is you just like leave your car parked, you take your bike, that's the best. I don't need reinforcement learning, we're done. But we want to kind of follow this velocity curve, that's the whole point. So in the blue in the background is the reference velocity, in the red is now one trajectory of one-time driving. There's different ways we can quantify this. We could have just a mean average error across the whole cycle, but this is actually regulated for us. There's actually, from the European Union, regulations on how you can measure how well you follow the velocity curve. And basically what it does is it defines a allowed velocity box for a given time. You have a time tolerance, you have a velocity tolerance. You're allowed to be anywhere within that box. If you leave that box at a specific time, that counts as a fault. If that fault, then there's a table of all these parameters, but if that fault lasts longer than a specific time, in this case 1 second, it counts as a fault. And you're allowed to have 10 of these counted faults. Not that important, but we have a measure of were we good enough or not on the velocity following. That's the take-home message here. And this isn't our invention, this is all, I mean, you could read it up in this regulation. And for reference, so how does this MATLAB optimized algorithm kind of score up? It has a fuel economy of 38.76 miles per gallon for a particular driving cycle that we're using with 8 faults. And on the left-hand side, you see the velocity from the car. You can't really read anything from this because you don't know what it was supposed to be, but it's not bad. And the policy, so the actual gears that it's used is on the right-hand side. So you can see it gets to a higher gear for the higher velocities. That's quite intuitive. Shifts down when it needs to accelerate. I would say it's very intuitive, an intuitive policy. And like I said, that was for one driving cycle. The driving cycles are also regulated, so we're not making those up either. There's one called the federal test procedure, and that's the driving cycle we're going to be using for training. That's what MATLAB also uses for training. We just picked one that's the one we chose. We're also looking into training on maybe multiple driving cycles, but we haven't got to that point yet. But there's a total of 11 driving cycles, and we're using the other ones for testing and evaluation in the end. Okay, so now to get to kind of what we actually did. So that's sort of the use case setup. And our goal is to make this, like I said, we don't want to implement a neural network because it's just hard for companies. We want to make this whole engineering process as simple as possible. So what we did is we took the MATLAB simulation. We didn't work directly in MATLAB just because we have a lot more experience in Python, to be honest. There's a lot of libraries which are available in Python. I know you can use some of them from MATLAB, but we've never done it. So our kind of simple way out was to just compile the MATLAB simulation into a DLL. You can run that via step function from Python directly. And we packed this step function into a gymnasium environment. I'm guessing you all know and have used gymnasium environments. It just makes reinforcement learning very simple. It gives you the whole structure. And included in that gymnasium environment is our reward function that we implemented. And that's just a trade-off of the velocity following. Here we actually used the mean average error at a specific point because it gives more information than just the number of faults. You lose a little bit of information that way. And then the fuel economies on the right-hand side, and the way it's in the reward at a specific time is the actual sum of the fuel flow at all of the points since the last reinforcement learning update. The simulation has an update time of around 2 milliseconds. Our reinforcement learning updates are around half a second, and the fuel flow is very, the timescales are very short. And so if you only were to look at the fuel flow at the moment of the update, you might have missed something that has a big impact on the reward. There's one free parameter which helps guide the training in terms of how much does the velocity and the fuel flow kind of compare to one another. Also has to do with how you've normalized these values. That's something we've set in the training. One advantage of gymnasium environments, you can use stable baselines super easily. To be honest, it's just so easy to use. We wrote our algorithms at the beginning of this, and stable baselines were always better. Nothing much more I could say. So yeah, that's great. We use PPO, but again, it was just to use one algorithm. In the end, in any case, for all these industrial applications, it should be irrelevant what algorithm you should use because the situation shouldn't be that complex. We used for our experimental, like keeping track of the experiments, hyperparameter tuning, we used the program weights and biases, just again out of experience. And this is what kind of the results we got. These are all trained policies. And on the x-axis, you see the fuel economy. The y-axis, you see the velocity error. This is now the mean average error. And what you see is that we find many different solutions. And if you go back to the reward, even if you fix alpha, you can have a very similar reward by trading off fuel economy and velocity following. So that's what you see here. There's kind of this linear trade-off. We have many different solutions. And we have a set, I think there's like 33 points here. And if I were to implement a neural network, then I would just go to my application engineers and say, well, what point is better for you? You know, like how important is fuel economy versus the velocity following? We could implement that directly. Here's this, just the velocity following translated to the number of faults. You just get done a couple of steps. But we don't want to implement the neural network. So at this point, our next approach is to take these neural networks and try and write down a lookup table, translate them into a set of rules, and see how good we can get at that point. And again, for reference, our MATLAB had a fuel economy of 38 and 8 faults. So all of the solutions here are better than our benchmarks. We take this as a base kind of set of good policies for us. Yeah, so like I said, so from this point, we can now kind of go into the second point, which is addressing the explainability of all of these networks. Just kind of a side note, before we started this project together, the people at Bosch did try and implement a Q table from scratch, like using Q learning, because then you have your table in the end. But they ran into problems like you have to, all our inputs are continuous. They had to discretize the continuous variables. They didn't know where, like you have to kind of optimize where those breaks are. Training is not very efficient, and they never obtained a better policy. So they kind of scrapped that idea then. So what is our method? Train the RL agent, that's what we did. We have a small state space. We ended up, so we could sample the policy network directly. This isn't always true. There's ways to get around this. we haven't looked at in this project. I think it's important and something to do in the future. Based on this, then we have a fixed data set. We can train a decision tree like everyone does in standard machine learning classes. And there, what we've done is, because we're interested, we know when you have a complex enough decision tree, I mean, you could basically reproduce a neural network at some point. But we're interested to see how simple can we make it. You know, where's our trade-off between accuracy and explainability, and can we see that progression, and is that generalizable? So we train for each of our networks. We train a set of decision trees, increasing the depth each time, and then evaluate them independently as a lookup policy on our different driving cycles. Okay, and so these are the results. This project is still work in progress. We still have a year left in the project, so I don't have final results. That's why I'm kind of interested to present it here at this conference, maybe get some feedback. This is what we have until now. So like I said, we had around 30, I think between 30 and 35 trained neural network policies. For each of those policies, we train 20 decision trees, one for depth 1, 2, 3, 4 to 20. So at each depth here, I have in these boxes around 30 to 35 points. And I have then tested or evaluated these policies on the training algorithm for this plot. And then I look at the resulting fuel economy, and I see that in relation to the fuel economy of the underlying neural network. Because those neural networks all had different fuel economies, I take this ratio so that I can compare them to each other. And what you see is that actually the behavior is pretty well behaved. That was the first positive thing to see. For the small trees, you get a much larger distribution in the behavior. That's, I think, to be expected. For us, it was interesting to see where that kind of convergence occurs, which I would say here is like around depth 7 to 8. For a depth of 7 to 8, that means you have like 2 to the power x final nodes in your tree, just as a reference. One thing that's interesting is the points that are above. I don't know if I can. These, like this set of points here, they all come from the same neural network. I'm trying to understand why they're so much better. I still haven't really understood why. Like this kind of better performance is robust against how I sampled the network, how I trained the decision tree. I'm still not really sure where that's coming from, to be honest, but that's something I'm looking into. The one isn't a higher bound because you can, by chance, have a little bit of a different policy, which is better. There's like one isn't an upper limit. You kind of get lucky that way, but I don't really understand why it's so much better there. I'd like to have a better understanding of that. But this gives us a little bit of confidence, I guess, that also you're not just kind of, I was a little bit worried you train the decision tree and have totally random behavior a little bit, so that these boxes would be way bigger all the way up to depth, like to much higher depth. So I think this is kind of a promising first step. Like I said, those were all evaluated on the driving cycle that we trained the neural network on. And now I want to evaluate that with all of the driving cycles that we have at hand. So we have a total of 11 driving cycles. This FTP cycle, this was this federal test procedure where we did the training. So if you see the red lines, that's where the benchmark is. The blue, purple ones, those are the reinforcement learning agents. And you see all of the agents are better for the FTP, and that's because that's how we chose them. I mean, that's where we trained them on. We knew this in advance. So interesting is how the reinforcement learning agent policies perform on the other cycles. For us, the positive things is they generalize quite well, so they perform a lot better than the benchmarks in most cases. And you see the worst performance are on 2 distinct cycles, at this one here and this one here. Those ones are highway cycles. So these driving cycles have specific properties. Those are 2 highway driving cycles, and the one we trained on is a lot more kind of city driving with lower velocities. So we see here that the agent hasn't really learned the best policy for highway driving, but still it's not always bad. So I would say around half of or even more than half of the policies are still better than the benchmark. Now what's interesting though is to add the decision trees to this plot and see how those perform. I don't add all the decision trees from 1 to 20 because then it gets really hard to visualize. I just chose a set 2, 4, 6, 8, 10 to kind of see the progression. Excuse me. Again, this FTP, this is what we saw in the previous plot. So you see how the distribution of the points kind of gets smaller and smaller as you increase the size, which is as we expected. But interesting is to know at what size that kind of decrease in the distribution becomes. And also that the decision trees tend to generalize just as well as the reinforcement learning agent. So even for these small decision trees, the behavior is a little bit worse than the reinforcement learning, but that only stays for maybe the decision tree size 2, 4, and then you have quite comparable performance, roughly, I would say. And again, all this, like, what is comparable performance? I'm giving this like on an industrial kind of benchmark where kind of the 80% solution is okay. So not every decision tree was better than the benchmark. Not every decision tree had the same performance of the reinforcement learning agent, but I would say the general tendency is in that direction. So it gives at least a motivation to maybe try this as a method. Maybe my last point is that in these I actually kind of found it hard to know how to visualize all of these results. And for example, in this plot, it's hard to see which points belong to which. Like maybe the reinforcement learning policy was here and the decision tree, which is, you know, from it is way down here. That would be pretty bad policy. I'm kind of assuming that the points are next to one another. And so one way I'm trying to visualize that is to look at, for a specific neural network policy, was I able to find a decision tree which outperformed the benchmark in every single cycle? And how many cycles was it able to outperform? And that's what I'm trying to show here. So on the x-axis is how many for each policy. So there's a point in these histograms for every neural network policy, and the point gets added to when I look at how many cycles was better than the benchmark for a decision tree trained from that network. I hope that's understandable, but it means that there were 6 neural network policies where, when I trained the decision tree, it was better than the benchmark for all the cycles. There was 2 cases where it's better than for 10 of the cycles, and so on. There was 9 neural network policies where the decision trees were better than 6 of the cycles. I have now like statistics with N30 for anyone who does particle physics. That's like, you know, it's pretty laughable. It's just hard to get more data points here. And what I was interested to see is, was this totally flat? Was there a lot clustered around like 1 or something? So again, this is, I think, kind of promising from what I was expecting. And the last point is that the smallest decision tree which outperformed the benchmark for all cycles in the fuel economy and the number of faults was a depth 5, which is 2 to the power 5 number of nodes at the end, which, for example, at Bosch, you could implement that in their control software. My last 2 slides are just an example of a good policy, just so you can see what it looks like. So this is an agent had a fuel economy of 46, 8 faults. The decision tree with a depth 3 had a fuel economy of 40.8 with 0 faults, and the MATLAB benchmark again, just for reference. And what does the lookup table look like for that decision tree? Then it's quite small, quite well contained because of the depth so small. And you just see there's, in terms of vehicle speed, you just have these 2 kind of, I don't know how they call it, like division lines where you break up your inputs. For the engine speed, you have these 4, and the pedal position, you have just 1, which is actually just in the middle. We can compare the policies directly. So this is for the FTP driving cycle. What did the shifting look like? And you can see right away, our solutions spend a lot more time in the higher gears. They have a lot more shifts than the MATLAB policy has. And I think that also reflects the MATLAB policy is influenced by this kind of your intuition that you maybe don't want to shift that much. I'm not sure exactly how that entered, but I think those are the 2 kind of take-home messages here. So in conclusion, what do we try to do? We try to sample the neural network policy to build up decision trees based on that. I think this could be a method to create kind of user-friendly policies for small state spaces. Obviously, this isn't scalable, our sampling policy, but there are ways to not just have to sample uniformly. I think we want to try that out in the future for a different use case. And despite the small tables, there's still improved performance. And I think in some of these industrial use cases, they're maybe not that complex that you really need fundamentally a neural network behind it. But we could still use the neural network to help training, help kind of automate training in that way. So yeah, thanks for your time, and I'm happy to answer any questions.
So if for the decision, given that you're going to train these decision trees, why not just use the decision tree as your model in the RL? And why not just train them? Why go to the neural network in the first place? Why not just train a decision tree? Like use decision tree as your model in your.
I mean, you could like build up your like a database in that way. The neural network is like kind of an easy way to get there, in the sense that, I mean, so from our simulation, you could just start sampling data from scratch and kind of create a giant database that way. The neural network kind of simplified that process. In the sense, the neural network is for us just kind of a way to distill the simulation into a static database of a good policy. Does that make sense? Was that your question?
Yeah, I guess it's, yeah.
I mean, you could use maybe your question was like, you could use your decision, you could try to update the decision tree in the reinforcement learning process.
That's what I mean.
We didn't try it, to be honest. So there's ways, I read some papers where they make like a decision tree differentiable and they update the decision tree that way. We just didn't try it. I don't know if it's better or not. If people have experience in that and try to like compare them both. So this seemed like, I mean, the thing that was cool about this is that stable baselines is a really good algorithm. So you kind of can just use it and it works. The algorithm or the papers I read where they found these like differentiable decision trees, it seemed they were a little bit more on the research side. Maybe they worked better, maybe not. Like I just didn't try it, but this seemed like a pretty like stable solution.
Regarding also the decision trees, what exactly is a decision tree? Do you mean like hard-coded values like between this and that?
I mean hard-coded values, there's a decision, so those like...
It somehow has to also combine all these inputs, so it combines the revolutions of the engine and...
Yeah, but the decisions are made based on one, so I would say maybe the first decision is, I never printed out the decision tree in, but maybe the first decision is on the pedal position. So first you split with respect to the one input, and then you split with respect to the second input, and then...
But how you can get a different depth? Because the way you described it always has the depth from the number of inputs. Or
no, the depth was something I put into place when training as like a fixed parameter from my side. You can make with the same input, you can make several decisions. Because first I could ask, is it greater than, I don't know.
Okay. Because I was wondering, like the neural networks, if it was a radio network, is it kind of similar to a decision tree?
Yeah, in the case that at some limit you have the same number of parameters, it doesn't matter what you use, it's the same number of parameters. Like you could have a set of rules. Your neural network is just a really complex set of rules. It's easy to update and differentiable. And there is a limit where all these things become the same, because if you have that number of free parameters, it doesn't matter how you store it a little bit.
You can manipulate the decision tree. You clearly see the decisions which you don't see.
Yeah, and the fact is, yeah, we wanted to, you could also just try to make a neural network with only, 2 neurons, and then you can mathematically write down my input is this, that means my output is this, because my weights are this and this. Or this is kind of like the black box approach. I don't want to know anything about I don't want to know how the neural network works. I don't want to know, I don't want to have a million parameters in my decision tree. So could I just use a neural network with a lot of parameters, get a small decision tree where I can look down for every input that I have and find. So if I go into that and someone asks me, why did I go do that? I can tell you, well, it's written like this in the table, and that's what they need to have.
And how do you convert the neural network to a decision tree?
Yeah, that's what I meant, is that we sample the neural network, the policy network. We basically do a uniform sampling of it over our input space, which is a very not scalable method. But we did it because it's small enough in our case. Okay. And then I also saw some people there's smart ways to do that sampling. If you can't just, this is kind of the dumb approach a little bit. And there's smarter ways to do that where you say, I don't have, it's not feasible for me to sample my entire state space. I want to do that in a smart way, and there's ways to do that in the literature. And I think that's something that you have to do because this is not a scalable solution what we did. So we would have to also try that with something like that.
Well, thanks for the presentation, very interesting project. I faced a similar problem months ago. We have to improve the explainability of a reinforcement learning controller. We also did this strategy with decision trees, and very useful trick for reducing the dimensionality of the models and hence the depth of these trees is to use sub values. I don't know if you know which is this. So it's basically it's a technique to measure the importance of the different variables for the decisions of the agent. So those variables which are not important, you can prune them. So your decision tree, your model in general is simpler. So I recommend you to use it because in our case it was very useful.
You can do this even automatically in other tools to do so.
So you only need your trained model and you plug it into a library which is available in GitHub.
Or in SAP.
But then you get out, so what is the output? You give your policy network in, and what are the...
No, you get an importance analysis. What was the most important input? What had the most impact on the
Okay, so that's to help you select
variables?
Okay.
Exactly. Variable importance.
Okay.
PCA for nonlinear or what? PCA?
Yeah, you get it out of the model. PCA is a better information process. So,
So a very nice way to discretize continuous variables is style coding. Did you attempt to do this?
No.
I think you mentioned this in the beginning that they tried it already at Bosch.
Yeah, I mean,
you have a discrete set and you optimize really the split points.
yeah, I mean, they tried to do it. Like in all the stuff we showed here, we didn't do it. We tried it at the beginning. It didn't work very well. They kind of did it before we started this project together, so I don't know all the details. I just know they ended up being in a place where it didn't work well, and then they always had to make finer, like a larger and larger table, and then they ended up never converging when they were training it. I don't know if the problem was in their algorithm they were used for training. I don't know if it was in their breakpoints. There was, I think, still too many open questions.
There's also adaptive type coding.
Yeah, and what we wanted to do was then use these, like we had in the end, we have some, like now we know what we could use. We should be able to reproduce it, and now then we can rule out that the algorithm was not working well. We just haven't got to it yet. So in principle, we should do it. And yeah, sorry, one last comment is I don't actually know. I've never spoken with an application engineer at Bosch, and I don't know how much, they must also have advanced techniques in creating these tables nowadays. I think it would be interesting to talk to them because they must have some solutions also for finding these.
Yeah.
We have half an hour break later, so we can ask her questions.
Yeah, thank you very much.